Okay, this is a lesson on paired samples hypothesis testing. This is the second question that we're going to go through, and we're going to try to go through this pretty quickly. So, a doctor wants to know if blood pressure medication is effective. There are 6 subjects who have their blood pressure recorded. After 12 weeks on the medication, the same 6 subjects have their blood pressure recorded again. For this test, only systolic pressure is of concern, and you should test at the 1% significance level. Okay, so here's what we're going to do. We've got the information right here, 161. We've got the blood pressure before, we've got the blood pressure after, and we've got all 6 patients. Okay, and so if you go to the decision-making tree, we're going to... Okay, so we have the decision-making tree here for hypothesis testing, and we have to ask ourselves a question. Are we dealing with continuous data from samples in a population, or are we dealing with frequencies, counts of categorical data? And we're dealing with continuous data, okay? So then are we examining the difference between a sample and a population, or examining the difference between groups? This is a little confusing because you're like, I don't know what we're doing. We're not looking at 2 different groups, but we are actually looking at 2 different groups. We're looking at a group of tests before taking blood pressure medication, and we're looking at the same group after taking blood pressure medication. And so we're examining the differences between the same group at 2 different times. Are the same participants being tested more than one time? In other words, do you have 2 values that are being compared? And the answer is yes. And so the next question is, how many groups do you have, or categories of values? And the answer is 2. So we have before and after. And so now that brings us to the paired samples hypothesis test. And you can go through step 1 through 6 in order to be able to determine that. Okay, now that we've determined what type of test we're doing, let's go ahead and do some of the calculations. So we are dealing with the before and after scores, and there's what we're going to do is just go right ahead and copy these, Control C, and I'm going to bring them right into Excel. I've got my fun little sheet right here, and I'm just going to paste them right in here. And so I've got the patient A, B, C, D, E, F, so all 6 patients. We have their before and we have their after scores. And then right here, in just a minute, we're going to calculate their difference scores and their means, so on and so forth. So, but let's go back to the Word document and make sure that we know exactly what it is that we want to know. Okay, so what is it that we want to know? What we want to know is this drug, is this blood pressure medication, is it successful in decreasing blood pressure, right? Is it effective in decreasing blood pressure? So we're going to write our null and our alternative hypothesis. And so our null hypothesis is saying that the mean difference is going to be less than or equal to 0. So the mean of the difference scores for the individuals participating in the drug study is less than or equal to 0. And then the alternative hypothesis is that the mean difference is going to be greater than or equal to 0. In other words, the mean of the difference scores for the individuals participating in the drug study is greater than 0. So just to be completely transparent with you, the reason why I kind of changed in the middle of this fun little recording is because I messed up the first time that I put this together, and it is really easy to mess up a question like this. So just really be paying attention. And when I say I messed up, it's really easy to mess up the tail. I messed up the tail when I put this together, and so you look at this and you see, okay, is the blood pressure going down? Is the blood pressure going down? And in my mind, it's like, if it's going down, then the score should be less. But in actuality, what we're saying is we are comparing the before to the after. So the question is how does the before score relate to the after score? And what we're saying is that the before score should be greater than the after score if there truly is a difference. And so that's the reason why you really got to be paying attention. It's like, what is it that we're actually doing? We are saying that the before score should be greater than the after score if the medication is truly making a difference. And that's the reason why you're looking at this right here. You're like, oh, the mean difference, we're expecting the mean difference to be greater than 0. And the answer is yes, we are, because the medication should help to decrease, which means that the initial is going to be higher. So what is the level of significance? Coming from right up here, still 0.01. And now we're going to get into test statistic, upper, lower, so on and so forth. So what is our test statistic? Well, coming up here, once again, do we have the population standard deviation? No, we do not. We've got 6 subjects, so therefore, we don't have a degree of freedom above 200. So our test statistic is going to be T, because the sample, there we go, because the sample size is only 6. Is this going to be an upper, a lower, or a two-tail? Well, we just answered that, and it's actually going to be an upper. Even though it really seems like it's going to be a lower the way that it's phrased, it's actually going to be an upper. And then also the alpha of 0.01, which is the same as the level of significance. And then if T, what is the degrees of freedom? Degrees of freedom, so this is really a little bit of a departure from the independent. With the independent, what you would have is, you've got 6 before, 6 after, and then you would subtract 2 for the number of categories that you have. But we have a paired, and so for a paired, you take the number of the difference scores minus 1. So there are a total of 6 difference scores minus 1. And so for that, the number of difference scores minus 1, so the degrees of freedom is 5. And so now let's go back to Excel. Instead of just saying, hey, this is a critical value, let's work all this out, okay? So we have the difference scores, so we're going to take equals the before minus the after. And so you've got all these different scores. Oops. Okay, there we go. All these different scores. And then we also have the mean equals the average of everything that you got here, of the before scores. And then you've got the average of all the after scores. But we're not actually comparing these two. If we were doing an independent samples, we would be comparing these two, but we're not doing independent samples. We are doing paired samples. And so what we're actually comparing is the mean of all of the difference scores. Okay, so I just took the mean of all the difference scores. Next, we can calculate the critical value. And there are multiple ways to calculate the critical value. We can go with the most traditional way of calculating the critical value by pulling up the t-chart. This is not the t-chart, this is the z-chart. So let me see if I can get the t-chart really quick. So there we go, t-chart. So we've got the t-chart right here. And remember, we've got a degrees of freedom. The degrees of freedom that we have is 5. So we've got 5 degrees of freedom. And the alpha is going to be 0.01. 0.01 for the alpha. And so remember the level of significance for a one-tail, for a two-tail, and then the one up here is a confidence interval. So level of significance for a one-tail with a 0.01, and we come down to degrees of freedom of 5. So it's going to be 3.365. 3.365. And so we can put that, oops, 3.365. The other thing that you can do is use this t dot inverse and then put the probability in the degree of freedom. So we're going to do equals t dot inverse, okay, and then the probability, well, what is the probability that we want? What is the alpha, the probability of having type 1 error, which is going to be 0.01. and then the degrees of freedom is 5. And it's going to give you negative 3.36493. The reason why is by default it gives you the cumulative, which means that it's going to give you the negative. So if you want the actual critical value, you just have to multiply it by -1, or okay, and so this will give you the critical value of an upper tail test. So the previous one gave you a critical value of a lower tail test. Okay, and so coming down here, like I said, the probability that it was asking for was 0.01, which is the same as alpha. The probability of type 1 error, which is 0.01, and then the degrees of freedom is 5. And like I said, it defaults for a lower tail, so to change it to an upper tail, just multiply it by -1. Next thing that we're going to do is there is definitely a better or a quicker way to do this, and that's by using the data analysis tool. And so I'm going to use that data analysis tool. I'm going to go to data, and you guys should have downloaded this. So data analysis, and you go to t-test for paired samples to samples for mean. So I'm going to click on that. You might need to scroll down to be able to get to it, but paired to samples for mean, press OK, and then you highlight the variable 1 range. So this is variable 1, and it can be horizontal, it can be vertical, does not matter. And then variable 2, so we're going to variable 2, the after scores do not include the mean, just include the before and after. And then the hypothesized difference, we're just sticking with 0, alpha of 0.01. Does it include the labels? Yes. And the output range, where do I want it? I'm going to come down here, say, hey, I want it right there, and then I'm going to press OK. So now I've got the, this right here is the results for running a paired two samples t-test. And so you can actually use all this information. It's very reliable. It gives you the t-statistics, gives you the degrees of freedom, gives you the Pearson's correlation, which you don't have to worry about that right now, the variance, the means, the number of observations. And then it also gives you the probability for a one-tail, probability for a two-tail, and the critical values as well. So that's really great. And so coming over here, I'm going to do something really quick. I'm going to calculate the margin of error. And so, we've got the numbers 6, the mean is 1.33, and then you notice I don't think that it gives you, let's see, standard, nope, it doesn't give you the standard error, so we've got to calculate the standard error. So we calculated the standard deviation of right here, of the difference scores. So we've already got the mean of the difference scores, so I'm going to do equals standard deviation of the sample. And for some of you, you're going to have an issue with doing that. Sometimes it doesn't like doing smaller samples, like 5 or 6, and you might need to do it by hand, but it gives me the standard deviation. And so I put the standard deviation in right there. Then in order to get the standard error, just take the standard deviation divided by the square root of n. And then the t-crit, we already determined there's a couple ways to get it. You can also get it from the data analysis tool. You can get it from the t.inverse with probability and degrees of freedom, or you can get it from the t-chart. And then next we're going to calculate the margin of error. Now this margin of error is a little bit different, and the reason why is because it's a one-tail test. So, with the margin of error, yes, if you're like, hey, I want an alpha of 0.01, and I want a margin of error, a 99% margin of error. But with an alpha of 0.01, remember, you're putting the probability of type 1 error all on one tail. So if you're putting 0.1 all on one tail, the margin of error of 98% actually takes care of that. It's kind of unique the way it does that. And so what I'm going to do right now is with the margin of error of 98%, you can actually pull up the t-chart and do margin of error with 98%. and come down here for, uh, margin of error with a one tail. Okay, so you notice confidence interval of 98% is the same as a one-tailed test of 0.01. So that's just really kind of unique. It's not unique, but just interesting to think about. And so it gives you the same t crit value. So we've got the same t crit value, and so the actual margin of error that we're going to get is you take the t crit value and you multiply it by the standard deviation divided by the square root of n, or in other words, by the standard error. Take the t crit, multiply it by the standard error. And what we're saying is that when we calculate whether or not it is statistically significant, or if we reject or fail to reject the null hypothesis, we have to overcome this margin of error. That's what we're asking to do. We have to overcome this margin of error of 2.55774. And in order to do that, what I did here is I made a 98% confidence interval. And so if we overcome the margin of error of 2.55774, this the lower level of the confidence interval is going to be greater than 0. So I can already tell you right now, because the lower level of this 98% confidence interval is not below or is not above 0, we're going to fail to reject the null. We don't care about this right here at all because it's a one-tailed test. We only care about the lower portion of that. So, but you're probably like, hey, I hear what you're saying, but I don't understand what you're saying. I'm so glad you asked. So this is a visual of it, right? This is a this is the margin of error, the lower level of a 98% margin of error, and so that's negative 1.2244. This is 0 right here, and this is the distribution. In order to reject the null hypothesis, we would need it to look like this. It would need to be past this blue line. It would need to be past 0 because we're testing it against 0. We're testing, how off our data might be compared to that 0. And so I can already tell you, because this is below 0, because the margin of error is below 0, that we're not going to reject the null. We're going to have to fail to reject the null. Okay, so we've got an upper alpha of 0.01, degrees of freedom of 5, critical value of 3.36493, which, I got directly from the t-critical one-tail test from the data analysis tool. And so coming down here, what is the decision rule? The decision rule is we are going to fail to reject the null hypothesis if t-calc is less than or equal to 3.36493. So we're going to reject it. We're going to reject the null hypothesis if t-calc is below this number. We're going to we're going to fail to reject it if it's below that number. We are going to reject the null hypothesis if the t-calculated value is above 3.36493. And so I went ahead and took the liberty of, putting t-crit right there. So t-crit is 3.36, and so if the calculated value is above that t-crit value, we are going to reject the null hypothesis. But what is it? So I'm going to go ahead and bring this up here, and I'm going to put t-calc right about there. And so we need to put, what is t-calc? What is t-calc? Let's go back over here, and so we're actually going to find t-calc, and t-calc for a one-tail test, let's see here, the t-statistic is 1.75412. 1.75412. So I'm going to go ahead and put it right here, equals 1.75412. And let's make this a little bit smaller so you guys can actually read that. Let's see, 10. There we go. So that is t-calc, and then you've got t-crit. So t-calc is not more extreme than t-crit. So they're both drawn here, and it shows, yes, it is above you know, a little bit, but it's not as far as what it needs to be. It's not beyond that T crit. Um, and so now we're going to formulate our decision with comparing the two of them. You can also calculate T calc by hand by taking the mean difference score and dividing it by the standard error. So let me show you how to do that really quick. So I'm going to come right here. We've got the mean difference score, which is right there. Okay. And then we got the standard error. So this right here is the standard deviation. And so equals the standard deviation divided by the square root of 6. So that's the standard error. And so now if we take the equals the mean of the difference score and divide it by the standard error, that's going to give you your t calculated value, your t calculated value right there. So let me show that to you one more time just to make sure that you guys like, hey, how did you do that? Very specifically, you have the difference, the average diff score divided by standard error. And that will give you your T calc value. Okay, so coming back to the Word document, we've got the critical value right there, like we said, and then we also have the calculated value of 1.75412. So I'm going to put that right there. Okay. So what is the value of test crit? What is the value of test calc? Compare the two and decide whether or not to reject or fail to reject the null hypothesis. And so we're just looking right at the decision rule that we made earlier. And based on this decision rule, we can more or less conclude that we are failing to reject the null hypothesis because there's not enough information to determine that there actually is a difference. And so what is the p-value of that? You know, we already talked about that, you know, with 1 minus so on and so forth. We did this in Excel for the probability of this occurring. So what is the actual p-value of 1.75411? And so what I'm going to do is I'm going to do equals, let me go back to the Word document really quick. So in order to calculate the p-value, what I'd suggest, you know, you can go to the z-table if you want to, but a much more accurate way of doing it is, number one, you can just go straight over here to the p, what's it called? You got the t-stat and the critical value, and then you've got the p-value of that t-statistic if it's a one-tail, and the p-value of the t-statistic if it's a two-tail. The other way that you can do it is equals t dot dist dot rt, and then we're going to put the t-statistic right there with the degrees of freedom of 5, and that's going to also give you the right tail t-value. And so that's what I would suggest you do is just go ahead and use that t.dist.rt if you're doing a right tail or upper tail test, or t.dist if you're doing a left tail test, or t.two-tail or 2t if you're doing a two-tail test. And so that'll give you the different pieces of information that you need. So we're going to go back and add to the probability worksheet. Let's see here. Or sorry, not the probability, the paired worksheet. So the p-value is going to be, whoops, 0.06 dot, 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 dot. It's not that it's extremely improbable, or that, sorry, it's not that it's not improbable, it's just that it does not go beyond the alpha. And the reason why this is really important is because, especially with medical stuff, with medical tests, it's like you want to make sure that it is like you don't want a 1% chance of being wrong, or I guess you don't want a 5% chance of saying, hey, it actually does something when in actuality it doesn't. So we really want that alpha of 0.01. And so because we have that alpha of 0.01, um, it's even though the probability of this occurring just by chance is like, less than 7%, um, we are comparing the alpha to the p-value, and we can determine that the results are not significant, not statistically significant, and also comparing the calculated value, the t-calc, to the t-crit right here, because the t calculated value is not as extreme as the t critical value. What we're doing is we are failing to reject the null hypothesis because the calculated value of 1.754 is less extreme than the critical value, and this is supposed to be positive, of 3.36493. So how would we interpret this for somebody that wants to know what's going on? The doctor should know that a sample of 6 patients did not indicate that the medicine was effective in decreasing, blood pressure. Conversely, the results, well, this is once again because I messed up the tail before. So I'm going to say the results indicated that the average difference between before and taking the medicine was a difference of 1.33, indicating that difference of 1.33, but this difference is not enough to be confident that there is an actual difference between difference in the average blood pressure, or difference in the blood pressure before and after taking the medicine. So that's how you would write that up for somebody that wants to know, hey, what is it that I'm actually doing? So that's a paired sample. Once again, be very careful because you'll get these all the time. I really try my best not to give them to you in such a way that you'd get turned around saying, oh, it says less, it says more, when really in actuality it's more than less, and it can be a mess. So just do your best to stay on top of that. So.